Hello, everybody. In this video, we're going to be talking about reactive systems that can exist in multiple phases. So we'll be combining a lot of what we've been doing with phase equilibria and chemical equilibria for reacting systems. And we'll go through an example which you'll work on in your homework. So to start, we'll talk about the phase rule and how we modify it to account for chemical reactions. So if you recall before, the number of degrees of freedom F equals 2 minus pi, where pi is the number of phases, plus n, where n is the number of chemical species. When we have chemical reactions, we subtract R, where R is the number of independent chemical reactions. In some cases, you may have a list of chemical reactions, but in some cases, if any two are a linear combination, can be combined in a linear combination to make another one, that means that they're not independent from each other. So if you have a system of equations, you need to reduce it to the number of independent chemical reactions. So let's go through this problem. We want to estimate the compositions of the liquid and vapor phases in a reaction of ethylene with water to form ethanol at 200 degrees C and 34.5 bar. So it's known that under these conditions, there will be the presence of both liquid and vapor phases. And you can verify that if you look at the phase diagrams of these species. The reaction vessel is maintained at 34.5 bar by connection to a source of ethylene at this pressure. Assume no other reactions. Okay, so the first thing that I did here was I wrote out the chemical reaction. Next, we can make some simplifications. We should always look for things that we can simplify and problems to make them easier. And in this case, we know, and we can verify if you're not sure by looking at a phase diagram, that ethylene or ethene, C2H4, under these conditions will always be a gas. So there may be some amount that's soluble in the liquid phase, but this is going to exist as a gas for the most part. So we can assume that the reaction takes place in the gas phase. We know that there's going to be, so we know that there's going to be a negligible amount of ethylene in the liquid phase. And even though the reaction is occurring in the vapor phase, water will exist both as liquid and vapor, as will ethanol. So this is important because if ethanol, depending on how much ethanol goes to the liquid phase, if the chemical reaction is taking place in the vapor phase, that will change the equilibrium in that phase. So throughout this problem, I'm going to use shorthand for subscripts rather than writing out the full name of the substances. I'm going to use the abbreviation E for ethylene, W for water, and ETOH for ethanol. Okay, so the first thing that we can do is identify the number of degrees of freedom in our system. You can go through this calculation yourself and you'll find it'll be 2. So in our case, temperature and pressure are specified. So we don't need any material balance for this. All we need to do is use phase equilibrium relationships. So we can consider reaction equilibrium and phase equilibrium considerations. So let's go into a little bit more detail here. So in the case of reaction equilibrium, we can use the equilibrium constant as we've done before. And that simplifies to the fugacity in solution of ethanol over the fugacity in solution for water times fugacity solution for ethylene, all times the pressure, standard pressure. So phase equilibrium condition is that for each species, the fugacity in solution in the liquid and vapor phase are equal to each other. So the fugacity in solution for the liquid species can be written as the mole fraction of that species times the activity coefficient of that species times the pure species fugacity in the of that liquid. And likewise, in the vapor phase, we can say that this is the mole fraction in the vapor phase times the fugacity coefficient times pressure. Again, just to remind you that the fugacity coefficient on the right accounts for non-ideal gas behavior in the vapor phase, and the activity coefficient on the left accounts for non-ideal solution behavior in the liquid phase. Okay, so we can substitute some of the things in that we have written so far. Okay, so that's just taking the expressions for fugacity in solution for the different species that we just wrote out and substituting them in. So what we are doing though is that we're taking into consideration that that when we have the fugacity of ethanol, water, or ethylene, we know that the fugacity in solution for each of these species in the liquid phase and the vapor phase are the same. So we can use either. And what we will find, what you would find if you were to try to solve the problem using all of these, is that it's convenient to use the liquid phase fugacity fugacity in solution for the water and ethanol phases, because there's going to be a non-ideal solution there. And for the ethylene, it's only in the vapor phase, so we are going to use the fugacity coefficient in the vapor phase. So just one note here is that these should have carets over the top. So again, we want to see if there's anything we can simplify. We can oftentimes assume that the effect of pressure is negligible on the fugacity. So for the case of ethanol, we can say that the fugacity of ethanol is the saturation fugacity coefficient times the saturation pressure. And these are both things that we can calculate pretty straightforwardly. Okay, so here's our equilibrium condition written out completely. So now we're going to address the mole fractions. How can we express these in other ways? So first, we can express the mole fraction of the liquid phase composition in terms of the other liquid phase composition. So for example, we can say that the liquid concentration of the mole fraction of ethylene is 1 minus the sum of the mole fraction of the other species. Only two of them are independent. The other thing we know is that the mole fractions can be written using our phase equilibrium constraint. Again, this is our extended modified Raoult's law with the non-ideal vapor phase behavior. So for fugacity coefficients, just like we've done before, we can use the equation of state to calculate these. Now we can express the mole fractions in our vapor phase in terms of other species using this modified Raoult's law expression. So rearranging this, we can see that we are writing the vapor phase mole fraction in terms of the liquid phase mole fraction of that species, pressure, and a bunch of fugacity coefficients. So saturation pressure in every case, we can calculate using the Antoine expression, just like we did before. At the given temperature, here's the number values I got. And you can use the equation of state to calculate the fugacity coefficients. So you can verify that using an equation of state. So for our equilibrium expression, if we start substituting these numbers in, we can simplify this down to this expression here. And we also know that the mole fraction of ethylene in the vapor phase, Y sub E, can be expressed in terms of these other mole fractions. Now, now that they're written as in terms of liquid phase mole fractions and activity coefficients, I'm substituting all the numeric values in here, and you can verify those. And of course, the mole fraction of water is 1 minus the mole fraction of ethanol, since there's only 2 species we're considering in the liquid phase. So the question is, okay, we have everything, or we have a lot of parameters now. What we don't have is any way to determine the activity coefficient of any of the species. So to do this, we need to identify a model for this. Okay, so I wrote the equations that we had again at the bottom of this page, just for reference. And what we're going to do is go through a general problem-solving strategy for this type of problem. So the first thing that we want to do is find a model for activity coefficient, or find some tabulated data in some reference. So for your homework assignment, I will provide a model. As you'll see later, this is going to involve an iterative solution, and doing an iterative solution using tabulated data certainly is possible, but it is cumbersome. So it is oftentimes in your best interest to do this using a model. Although I've done it before using tabulated data, it just takes time going back and forth between your equations and tables or graphs in some cases. The next thing that you need to do is calculate K from thermodynamic data. So again, just like before, using the Gibbs free energy of reaction, adjusting for temperature, I find that K is 0.003, and you should verify this yourself. So the next thing you need to do is you need to guess the liquid phase mole fraction of something. So we need to guess to start, and what will happen then is we will see that we automatically can get X. If you guess one liquid phase mole fraction, we'll get the other liquid phase mole fraction. The activity coefficients are a function typically of temperature and mole fraction in the liquid phase. So we can plug those into our activity coefficient model and then determine the activity coefficients using that guess. And then we'll calculate K using equation A that we have down there. That should, if our guess was correct, that should equal the same answer that we got in step 2. Of course, in your first guess, it's likely not true. So likely does not equal each other. So what you need to do is update your guess. So this is an iterative process until you converge, meaning that your guess of a mole fraction gives you an answer that gives you a K that's close enough to what you know it should be. Okay. So again, you can use MATLAB, Solver, and Excel. I've linked some resources for you to be able to do this. We will try to work out this problem, and I will provide you a model for activity coefficient. So that's all we have for now. And we will continue on from here. I think this will be the last video that we're covering for this topic. So there's less content here. We'll be focusing on problem solving, and please reach out to me if you have any questions, and hopefully I'll see some of you in office hours. Okay, see you next time. Bye.